Okay. So one more thing about u sub that we didn't talk about last time was when you have a u sub integral that is a definite integral. We did just a bunch of indefinite integrals last time to get through a lot of examples. So there's kind of a tricky thing that can happen that can be confusing when you have a definite integral. But the first step on this would still just be to find your antiderivative using a u substitution. What would be a good choice for u here? Things inside parentheses are usually good things. So I'm going to take the stuff under the square root. We know that as soon as you make a u choice, you're going to need to take the du, the derivative of it, which is really du dx, but we're always going to move the dx over to the other side. So my du is going to be 2x dx. And the bottom is the square root of u now. So I could write that as u to the 1/2. And let's talk about what the way I was presenting u sub last time as the most efficient way to get to where you need to be. Is the wishing technique. I wish I had a 2x dx left over in the integral, because then I could just change that in for a du. But all I have left over is an x dx. So I'm going to wish for a 2, and then compensate with a 1/2 outside. That was what we did last time on Monday. So that this turns into, the 1/2 will stay there. The 2x dx is now a perfect match. I can trade that in for a u, and I have u to the 1/2. Okay. So hopefully that part, and even if you don't do the wishing thing, if you do x dx divide by 2 and replace your x dx with du over 2, factor out the 1/2, you should get to the same spot at some point. But here's where things could get a little bit confusing, okay? If you do this, if you take these limits and you take the 0 and the 4 and put them on there, it's not correct. It's not correct. Who knows why? And I'll preface that with this. When we are doing a u substitution, we're committing to changing everybody. All of these things were all in terms of x. We're committing to changing everybody to in terms of u. And that's the problem, is even though with these definite integrals, we don't usually write it here, these are x limits. This is x equals 0, x equals 4. And so by doing this, we're mixing our x values with our u values. This is not really correct, okay? So when this happens, when you're doing a u sub with a definite integral, you actually have 2 options. She only presented 1, but you actually have 2 options. Okay, so I'm gonna show you how to do this both ways. Okay, so first of all, we have to say that this would be incorrect, right? How about I do this? Universal symbol, that is wrong, okay? So when this happens, here's your choices. You can either proceed with u substitution as we've been doing. I would bring this up and make that u to the negative 1/2 du, but just leave your limits off temporarily until we get it back into the language of x. So let's follow through this way. So antiderivative of u to the 1/2, I'm going to add 1, divide by the same power. Now, or you can flip that and make that a 2, but hopefully you see that that's going to actually cancel with the 1/2. And it's just going to be u to the 1/2 as my antiderivative. And what do we normally do after we do that is we plug back in our u, right? This is really now the square root of 9 plus x squared, because u to the 1/2 is really square root of u, right? Square root of u. Now that you're back in the language of x, it would be correct to go ahead and evaluate this from x equals 4 to x equals 0. And if you plug in, you're going to end up with the square root of 9 plus 4 squared. So 9 plus 4 squared minus the square root of 9 plus 0 squared. Let's just finish this off and then I'll show you the other way. This is 9 plus 16, which is 25. The square root of 25 is 5. And this is just the square root of 9, which is 3. So my final answer will be 2. So I'll put here 2 options. So over here, what I would say is just, I would say to describe this, I would just say leave limits off until back to x, right? Back to x. Until you do your u sub and you get it back to x, then it's okay to bring them back in. Okay. I'll separate these. Or the other option, and this is the one that you learned in class, which maybe means that's probably what she's going to do more often than doing this. I just wanted to show you that nothing's changed. We could still stick with what we're doing. Just know not to mix these x limits with the u u variable when I do a u sub. But the other option is to convert my limits of integration. That's what those numbers are called, the 4 and the 0. Convert the limits of integration in terms of u. Terms of u, that looks weird. In terms of u, there we go. And it's not that hard to do. Okay, it's not that hard to do. If you use your substitution, because we have this is our conversion right here. So I'm gonna point an arrow to here because that's our conversion from x to u or vice versa. So here's what I mean. I told you it was not okay to put these limits of 4 and 0 before because those were x limits. But if you could convert these to u limits, then that would be fine. And here's how you do it. If I take, let's start with this upper limit. If I take x equals 4 and put it through here, right? What would that mean u equals? That's going to give me, if u is equal to 9 plus 4 squared, that would give me u equals 25, right? And if I take my lower limit and run it through here, that's going to give me u equals 9 plus 0 squared, which is just 9. And so it would be okay to take the upper and lower limit and convert them so that this is 25, this is 9. I'm just taking these and putting them back into here. That is a 4 squared. Yes, it is. Because I was putting the 4 in here for x squared. And look what happens. So now when I find my antiderivative, we've already done it here. It's going to end up being the square root of u, right? So I'll just do it again. So it's 1/2 u to the positive 1/2 over 1/2. Those cancel out. So I end up with just u to the 1/2, which is root u. Here's the one advantage of doing that. If you convert your limits in terms of u, what do we normally do is we then switch back to x, but we don't need to. If you changed your limits in terms of u and you got this antiderivative, then you can actually just stick with this. You don't have to change it back to x and just put your u limits in there now. Does that make sense? And look what you get. If you plug in, you end up getting the square root of 25 minus the square root of 9, which is 5 minus 3, which is 2, which is exactly the same, right? Now, I will say this. I decided long ago that converting the limits of integration when you do a u substitution is not worth the hassle. And the reason why, here's the thing. What advantage do you gain? You see how I did it this way and see how I did it this way? Yes, you actually saved one step, didn't you? Because when you got to here, you didn't have to put it back in terms of x. So you saved one step by doing it this way. But was it worth the confusion? Because here's what usually happens in class, and you just have to be prepared for this. I was very specific, right? I wrote u equals 25, u equals 9. Up here, I wrote x equals 4, x equals 0. What usually happens in a class, okay, let me just take a piece of scratch paper. I'm just going to cover this up temporarily. Here's what usually happens in class. I mean, Professor Burke might be the exception. She's usually pretty clear. But what usually happens is a professor is working an integral like this, does some work on it, and all of a sudden they end up with this. When I go watch classes in person, when we go back in person, I'll sit in on lectures and I'll see professors like the integral starts like this, it turns into this, and I look around the room and everybody's looking at each other like and whispering, how did that 4 turn to a 25 and a 0 turn into a 9? Because most of the time they don't carefully walk you through converting the limits in terms of u. They just do it. And this can be very confusing, right? If all of a sudden the limits change. So however you do, but you should be aware, because I'm going to guess that's how you're going to be doing, that's how Professor Burke's going to be doing integrals when there's a u substitution involved. She's going to convert the limits. So, and it's easy enough. So it's worth learning. I'm just saying if that's confusing to you, just do it the normal way and just make sure you go back to x, okay? And unfortunately, well, now let's just leave it at that. I'm going to save this for this next problem for next time, because I want to get into integration by parts. And after watching class this last hour, I have a few things that I would like to remind you of that is going to make integration by parts much, much simpler. Okay, a few reminders before the next section. If you get an integral like e to the 3x, where it's just a constant times x, and this came up in lecture just last hour, one way to explain what your antiderivative is to do what I call this a mini u sub. Mini u sub. A mini u sub. And I say a mini u sub because we've done some substitutions where we've let u equal a whole big long thing. But in this case, all I would need to let u equal is 3x. That's a mini. That's a real tiny thing. du is 3dx. So I now have e to the u, right? That's my u. And all I have left over is a dx. So I would just need to wish for a 3, compensate with a 1/3 outside, and this turns into e to the u, and the 3dx is a perfect match. That just becomes du, right? I can just trade that in. Like 4/4 is equal to $1. They don't look the same, but they're equal. 3dx equals du, so I'm just going to swap it out, call it du. And we know our antiderivative of e to the u is just going to be e to the u plus c. And if I put my u back in, it's going to be 1/3 e to the 3x plus c. But are you okay with that? That can be explained with a u substitution. Now, having done all of that to get that the antiderivative of e to the 3x is 1/3 e to the 3x, let me squeeze another example in here. How many people have a guess for what the antiderivative of e to the -7x dx would be if I did a whole another mini u substitution? What do you think it would be? Well, that's hard to write in the chat. Oh, good. Maya was on it. How many people agree it would seem reasonable, since the antiderivative of e to the 3x was 1/3 e to the 3x, this would be -1/7 e to the -7x plus c, right? And so what we need to get, what will be really helpful for you is anytime it's just a constant times x, it's just going to be whatever your antiderivative formula is, and then you're just going to be doing 1 over the constant on the outside. So if you, to the extent possible that you can figure out that this is equal to this without doing all of this, your life is going to become much, much simpler. Okay, so what I'm saying is you want to be able to do these mini U subs in your head without actually writing out the U sub. And let me show you some more examples to show you what I mean. It doesn't just have to be E. We know the antiderivative of cosine of regular x is just sine of x. So if it's just a constant times x, I could do the whole mini U sub and let U equal 4x and do the du and all that stuff, but it's just going to come out to be, if the antiderivative of cosine of x is sine of x, it's going to be sine of 4x with a 1/4 out in front. If I had the sine of 7x, we know our antiderivative of sine is negative cosine, so this is going to be, well, 1/7. Now the negative is actually coming because the antiderivative of sine is negative cosine, so I'm going to kind of separate that. If I had secant squared of 1/5 x, what's your antiderivative of just regular secant squared of x? From 17a, whose function has a derivative of secant squared x? Do you remember that would be tangent? That would be tangent. So if the antiderivative of secant squared x is tangent x, the antiderivative of secant squared 1/5 x is going to be tangent of 1/5 x. Also, okay, kind of divided by 1/5 or like 1 over 1/5, right? Because that's what I've been doing here, but that's obviously going to just turn into a 5, isn't it? 5 tangent of 1/5 x. So that integral that came up in class today was basically her trying to explain that, you know, going back to something like this, that if you want to find your antiderivative of cosine of mx, like cosine of 4x, that it's going to be 1 over m times the sine of mx, right? Whenever it's just a constant times x, that's how you can do it. You don't have to run through the whole U substitution to get to the answer. Okay, so practice seeing that, because it's just it's gonna make your life easier, because these little mini U substitution integrals show up all over the place in integration by parts. And if you have to keep writing out the U sub every time it's just a mini U substitution, it's going to take forever. And I think we know on our 24-minute short test, right, we don't have a whole lot of time, so we want to be able to do things more efficiently. Okay. The other thing that I think would have helped, I kept seeing the question in class earlier, was how do I know how do you know you're doing integration by parts, right? How do you know you're doing it? And one answer was the answer she gave, which is true, was she said, well, I don't know any function whose derivative is this. But here's what I would add to that. Remember, it's been a while. It's been since the first day when we were doing antiderivatives, that whenever you have a product of two functions, you cannot just take the antiderivative of this one and multiply it by the antiderivative of this one and tag on a plus c. It won't work. It doesn't work for derivatives, right? If I said I had f of x is equal to x e to the x, and I said take the derivative, you know you can't just take the derivative of x as 1 and the derivative of e to the x is e to the x. That's wrong too, huh? If it doesn't work for derivatives, it isn't going to work for antiderivatives, okay? And of course, you could confirm that this is not true. If you took the derivative of this, it's not going to equal x e to the x. I'll let you do that if you want, but okay. So we'll keep that in mind too. And now let's jump into what your topic was today. because most of the time when you're using integration by parts, you are going to have a product most of the time. There are some exceptions most of the time. And what's going to be a challenge for you for your next test is that you can have, look at these two integrals. Both of these are products, right? I've got x times the cosine of x squared. I've got x times the cosine of 2x. They're both products. And one of them can be handled with regular u substitution, and one of them cannot. And you're going to have to be able to distinguish. So let's make that decision right now. Who has an opinion, if you've been practicing u sub, which one do you think could be handled with u sub, 3 or 4? Hang on 1 second, everybody. Okay, sorry, I had to step away for a second. Yeah, so let's try it. So if you were doing 3, I see 3 in the chat there, what would be a choice for you? And that, again, this is the hard part, I think, about for you guys, is that you haven't had a whole lot of practice with u sub yet. And so it's kind of hard to say which one's going to work out. But if I let u equal x squared, remember that a good indicator that u sub is going to work is that when I take du, that I see, right, if this is my u, what do I have left over? I have an x and a dx, and I see that right there, that I see what's left over there. So absolutely, this would be, if I called this u, and in order to convert this x dx to a du, what I want to see, what I'm wishing to see, is an extra 2 there. So I'm going to wish for my 2, compensate with a 1/2. The 2x combined with the dx becomes my du, and then I have cosine of u. And the antiderivative of cosine of u is sine of u. So it would be 1/2 sine, and then I put my x squared back in. Okay. But now, so that worked out pretty nicely, right? It was a product. Here's another product, but if you tried to do a u sub here, I mean, the only thing I could think of letting u equal is 2x. Du is equal to 2 dx. I could wish for a 2 there. I could wish for a 2 there and compensate, but notice I would have a leftover x, right? So if I tried to do this here, I'll just scribble it out. This would be, x would still be there. I would have cosine of u, and I could wish for a 2 and compensate with a 1/2. So I could turn that into a du, and there would be a 1/2 there. But notice I would have a leftover x. I would have this as leftover, right? There's no, don't have a conversion. Now, if you were here on Wednesday, we did a problem where sometimes it's okay to have a leftover x. If you go back here, x equals u over 2. But if I put that back in here, here's the thing. I could pull out that 1/2 if I want to, but notice I still have a product, don't I? I still have u and cosine of u, which I had at the beginning. I have x cosine of 2x. So trying to do a u substitution still doesn't get me anywhere, right? I still have a product, and I'm going to keep reiterating this because this is one of the more common mistakes. Remember that there is no way, I can't just integrate this one and integrate this one when I have a product. So that's not going to work. So this is where we need your new method that you learned, integration by parts. And your formula is, we'll go straight to it, the integral of u dv equals uv minus the integral of v du. This is your integral, the one you're working on. That's the one you're stuck on, your integral. This is your answer. That's how we're going to find the answer, by using the right-hand side of this. And so what we need to do is we need to think of, since this is our integral, we need to think of one part of this as some function u. And remember, dv is shorthand notation for a derivative. So we're thinking of one part as a u and the other part as the derivative of some other function v. And it doesn't necessarily have to be in order. Like, I don't necessarily have to have this be u and this be dv, right? It could be that this is u and this is dv. It could be. So what does that depend on? When I pick my u and dv here, I'm not picking it for the same reasons I choose u on a regular substitution, right? When I choose u on a regular substitution, I'm focusing on the derivative showing up somewhere else, but not when you're doing integration by parts. The way you should choose your u, choose u so that it becomes simpler when you take the derivative. Okay. Meaning, so here's my options. I could either let u equal x, in which case the derivative is 1, or I could let u equals cosine of 2x, in which case the derivative is like negative sine of 2x times 2. How many people agree the derivative of x is a lot simpler than cosine of 2x? So that is going to be my u. U is going to be x, which means everything that's left over has to be my dv. Okay, so in this case, but again, not always, this is my u, this is my dv. Our answer is going to be given by this. So notice that whatever I let u equal, it's going to be in my answer here, but over here, I'm going to need the derivative of u, in my answer. So then I'm going to do du. Du is just 1 dx, so du is just dx. And ready? Here we go. To get from here to here, this is the antiderivative. And notice, to find the antiderivative of cosine of 2x, that's like a mini u substitution, isn't it? It's a mini u substitution. And I don't want to, I've got a long enough problem already as it is. So you want to be able to just tell me that the antiderivative of this is going to be 1/2 sine of 2x. Does that make sense? And then I just plug into the formula. I'm going to rewrite it. uv, that's my answer. So I just pull, and uv, so it's going to be u times v, this times this, x times 1/2 sine of 2x. Minus the integral of v times du, this times this, 1/2 sine of 2x, and then times du, which is dx. Now, the formula still has an integral, but the idea is this integral should be easier to do than the one we started with, and it is. If I factor out this 1/2, here's yet another mini u substitution. I don't want to do it. I don't want to go through a whole u sub here, but so because it's just sine of 2x, I know the antiderivative of my sine function is negative cosine of 2x, but then I just multiply by the reciprocal, 1/2, negative 1/2 cosine of 2x. And then we just put the plus c at the very end. And of course, this could be simplified, right? This could be written as plus 1/4 if I multiply these together. Let's try another one. I want to try to capture both of these next ones. There we go. There. You can see the last two steps here and then my next two examples. So I like to do this because, as I mentioned earlier, the challenge is going to be you're going to get two integrals that kind of look very similar. And like I have here, here's two of them. And one of them can be handled with U substitution, one of them cannot. So think about 5 and 6 for a second and think about which one would U substitution, regular U substitution, work out for. Don't doubt yourself. You're right. Yeah, because with ln of x, if that works out nice for u sub, because whenever, if I let u equal ln of x, the derivative is 1 over x dx, which shows up in here, right? If I just rewrite this as ln of x squared times 1 over x dx, which is how I could rewrite that, then this is a perfect match. This becomes u squared. And this is a perfect match for du. I don't even have to wish for anything. And my antiderivative of u squared du in terms of u would be u cubed over 3 plus c, which is ln of x cubed over 3 plus c, done. But you can probably see now why this one is not going to work out with u sub, because if u is ln of x, I need to see a 1 over x dx, and I don't need, my x is in the numerator here, right? So you can see why this would not work with u sub, because I can't just create my du out of this. So whenever it's a product, and I'll remind you here, this was a product, right? It looks division, but you could think of division as a product. But so they're both products. But if it's a product and u sub doesn't work, then it's probably going to be integration by parts for this one. And when it's integration by parts, we have to choose a u. One of these is going to be u, the other one's going to be dv, the derivative of some other function. Now, this one's kind of a close call, because remember, my criteria for choosing u is which function is going to become simpler when you take the derivative. If I let u equal x squared, the derivative of x squared is 2x. I'd say that's simpler, right? I've knocked it down a power. If that was, but here's to me what is way better than that. If I let u equal ln of x, however, du is 1 over x. Now, why does that win out for me? How many people love working with logs? And you can't see me, but my hand is not up. I don't like dealing with logs. So having, if u is equal to lx, when I take the derivative of it, it becomes 1 over x. There's no more logs to deal with, right? And see, in my book, that wins out over letting u equal x squared and du being 2x. In truth, this is really the only correct answer. If you tried to do u equals x squared, you're going to get stuck. So in truth, this really is the only choice. You don't really have a choice. But that's how you could logically conclude that that's the correct choice, because it becomes a simpler function to deal with when you take the derivative. That means whatever is left over, x squared dx has to be my dv. And I'm doing my antiderivative here. So that's just, so we don't even write an integral. You just go straight to it. It's x cubed over 3, or 1/3 x cubed. And then my answer is always uv minus the integral of v du. So u times v minus the integral of v 1/3 x cubed times du, which is 1 over x dx. So it's going to be, to save a little time, I'm going to bring this down on the next answer. Remember, this is a product still, so you can't just find the antiderivative of this times the antiderivative of that. What you can do is pull out this 1/3. And if you have x, what is x cubed times 1 over, what does this simplify to? Isn't this the same as x cubed over x, which is just x squared? This is just x squared. And so it would end up being this stuff here. I might as well write it now. Minus 1/3, your antiderivative of x squared. We did this earlier, huh? That's 1/3 x cubed again. Plus c. Again, that could be written as minus 1/9 if you want to. Right. Here we go. One more time. Let's make a decision here. This is x squared e to the x cubed. And then the example after that is x squared times e to the 3x. One of those integrals, they look very, very similar. One of those integrals can be handled with regular u sub and one of them can't. So make a decision which one could be done with u sub and go ahead and do it. Opinions on which one can be done with u sub, 7 or 8? You know, and if you've been doing some integral practice, if you've got an integral with just one e in it, if u sub's going to work, you're kind of going for e to the u du, right? Because we know that antiderivative. So what's nice about integrals with e in it is if you're going to try u sub, there's pretty much just one option for your u, and that would be the exponent, right? If you're going to go for e to the u, you would want that to be your u. Yeah, and this one works because if u is equal to x cubed, du is equal to 3x squared dx, which I almost have here, huh? All I'd have to do is wish for a 3, compensate with a 1/3. And I've got 1/3 the integral of e to the u, and the 3x squared together with the dx becomes my du, right? That's du. And your antiderivative of e to the u du is just e to the u. Plug back in. and we're done. But the next one, you could probably see that if I tried letting u equal 3x, du would just be 3 dx, which I could make work. I could wish for a 3. But then what would I do with these x squared terms, right? What would I do with these leftover x squared terms? So if you get a product and u sub doesn't seem to work, then it probably is integration by parts. Which piece is going to become simpler when I take the derivative, x squared or e to the 3x? How many people agree x squared, right? E to the 3x was actually going to get a little worse, huh? The derivative of e to the 3x is 3e to the 3x. So definitely, I think x squared wins out here. Du is 2x dx. That means dv is going to be e to the 3x dx. And here's another mini u substitution that we talked about earlier. The antiderivative of e to the 3x dx is going to be 1/3 e to the 3x. So then it's uv x squared times 1/3 e to the 3x minus the integral of v du I'm just going to bring this down. And so what you have here is, let's pull out the constants. So there's a 1/3 and a 2. So you could pull out a 2/3. And I'm just going to put the x in front. Doesn't really matter where you put it. Because what I want you to see here is, while we have made progress, our original integral started off with x squared e to the 3x. The integral we're now encountering is just x e to the 3x. So I've knocked down the power. But notice this is still a product, right? This is still a product. And I don't think u sub is going to work, right? If I try to do regular u sub, I'm going to be stuck with that x. And u sub doesn't work. So what are we going to have to do again? For this, just for this integral here, we're going to have to do integration by parts. Yep. Therefore, so we're going to need, so we're kind of just focus on this right here. We're going to need a new u and a new dv. So we'll work right here. Well, last time letting the u be the x term was a good choice because that becomes simpler, which means my dv is going to be e to the 3x one more time. Derivative of x is just 1 dx, and my antiderivative 1/3 e to the 3x. One thing that's a little bit difficult on these when you have to do it twice is just making sure you're accounting for things, right? We still had this as part of our answer. So now I'm going to bring it back. So we have x squared times 1/3 e to the 3x. And don't forget, we're doing integration by parts just on this part, but that was being multiplied by negative 2/3. So we're going to have to do our different color here. When we do our uv minus the integral of v du, all of that's going to be multiplied by this negative 2/3. And so here we go, uv, so x times 1/3 e to the 3x minus the integral of v du, 1/3 e to the 3x times dx. Let's just leave everybody factored out for now. Okay, now, and then the other thing too is I heard everybody's like, whoa, overwhelmed. It was so long, right? Everything, the process was really long. And what she kept saying was, you're just rewriting things. You're just rewriting things. And what she means by that is the only work we really need to do here is finishing this out. So I am just rewriting this, right? That's what she meant. And so if you can, I don't want to write this again. So as you get better with this, if you can do some of these in your head. So what I mean by this is this 1/3 could of course come out of the integral, but then what would the integral of e to the 3x be? Wouldn't that be another 1/3 e to the 3x? Right? So if you can kind of do that in your head, so you don't have to keep rewriting all this mess, it's going to be minus 1/3, and then this antiderivative is another 1/3 e to the 3x. Then that's going to save you a little bit of time here. And then we'll usually just put the plus c here. This is actually fine. If you've got a WebWorks problem like this, just you could input it as long as you use parentheses in the right place. Alternatively, you could, make it a little bit easier to input if you do start simplifying things. So let me just do this last thing and then we'll be done here. Like I can tell this is going to be negative 2/3 times 1/3 is going to be negative 2/9 x e to the 3x. This is negative 1/9, but if I multiply that by negative 2/3, I'm going to end up with positive 2/27. Right, that's negative 1/9 times negative 2/3 is going to be positive 2/27. And so, if you have a WebWorks problem, it's probably going to be easier to plug it in like this than, in all these parentheses and brackets and stuff. But either way, it should be fine. How many people feel a tad bit better about integration by parts than you did an hour ago? I'll take a tad. That's fine right now. A little bit scared that I get that. Okay. All right, perfect. Okay. And believe it or not, there's more to this. So I don't know I'll have to see what the plan is for Monday, but we definitely need to practice. There's a few more types of integration by parts that we need to practice. Yeah. Stop recording.